What if you could walk up to a website, press a button, and control a real piece of lab equipment from anywhere in the world? That's exactly what we built. This is the parametric retrofit of lab equipment for remote control, and here's how we did it. The system has 4 layers. I built the web interface, the front door for any remote user. Bruce connected the Raspberry Pi control stack and wired it to the web through MQTT and Simulink code. Skylar retrofitted the physical apparatus so it could be controlled by a computer, and Angel set up the video pipeline so users can see the machine running in real time. Every layer talks to the next seamlessly.
This is the original Feedback Instruments control box. It's a great piece of hardware, but everything about it was manual. Switches, buttons, manual cart centering need a human standing right there. That had to change. We pulled out the analog control circuitry and replaced it with 2 ESP32 microcontrollers. One handles encoder position. It reads where the cart is at all times and streams that data to the Raspberry Pi over SPI. The other drives the motor through the BTS 7960H bridge. Forward, reverse, speed control, all software driven. Before every run, the cart automatically homes itself, finds center, confirms its position, waits for the control model to take over. What used to take a person standing at the bench now happens with a single command.
Once the hardware is ready, the Raspberry Pi 5 takes over. The Raspberry Pi runs a real-time control algorithm generated from a Simulink model and compiled into an executable for the Raspberry Pi. No MATLAB license is required, no PC is needed. Here is the data flow. The encoded cart position and pendulum angle are read by the first ESP32. The ESP32 sends the cart position and pendulum angles as a 12-bit value to the Raspberry Pi via SPI. Then, the Raspberry Pi, running the Simulink model, computes a motor control feedback value. This value is converted by the MCP 4725 DAC into a voltage which is read by the second ESP to control the cart direction and speed. Back on the Raspberry Pi, a custom Python daemon manages that DAC, handing control off when the module starts, taking it back if anything crashes. When everything is go, homing complete, model running, encoder locked, the status flags confirm it. The system becomes fully operational.
A remote user needs more than just controls. They need to see what's happening. That's where the streaming pipeline comes in. A dedicated Raspberry Pi captures live footage of the apparatus and pushes it over SRT to our Oracle Cloud server, where MediaMT is rebroadcasted as a WebRTC stream. That means sub-second latency video directly in the browser with no plugins, no downloads needed from the viewer. Then whenever the user opens the site, the feeds are live and real. And with the press of the start button, they will see the machine running over there in real time.
This is ScienceLabTU.com, the front end that ties everything together. From here, a remote user can see the live video feed, monitor real-time telemetry, cart position, system status, connection state, and send control commands directly to the apparatus. The interface talks to the Raspberry Pi through MQTT over our Oracle Cloud Broker. Commands go out, data comes back, and the page updates in real time. End-to-end, retrofitted hardware, embedded real-time control, live video streaming, and a web interface anyone can use. We're still hardening the system. PCB integration, full telemetry logging, pendulum balance, but the core pipeline works. Remote lab access isn't a concept anymore, it's running. Thanks for watching.